Maxwell's influence on the evolution of the idea of physical reality. The belief in an external world independent of the perceiving subject is the basis of all natural science. Since, however, sense perception only gives information of this external world or of physical reality indirectly, we can only grasp the latter by speculative means. It follows from this that our notions of physical reality can never be final. We must always be ready to change these notions, that is to say, the axiomatic basis of physics, in order to do justice to perceived facts in the most perfect way logically. Actually, a glance at the development of physics shows that it has undergone far-reaching changes in the course of time. The greatest change in the axiomatic basis of physics, in other words, of our conception of the structure of reality, since Newton laid the foundation of theoretical physics, was brought about by Faraday's and Maxwell's work on electromagnetic phenomena. We will try in what follows to make this clearer, keeping both earlier and later developments in sight. According to Newton's system, physical reality is characterized by the concepts of space, time, material point, and force, reciprocal action of material points. Physical events, in Newton's view, are to be regarded as the motions, governed by fixed laws, of material points in space. The material point is our only mode of representing reality when dealing with changes taking place in it, the solitary representative of the real, insofar as the real is capable of change. Perceptible bodies are obviously responsible for the concept of the material point. People conceived it as an analogue of mobile bodies, stripping these of the characteristics of extension, form, orientation in space, and all inward qualities, leaving only inertia and translation, and adding the concept of force. The material bodies, which had led psychologically to our formation of the concept of the material point, had now themselves to be regarded as systems of material points. It should be noted that this theoretical scheme is, in essence, an atomistic and mechanistic one. All happenings were to be interpreted purely mechanically, that is to say, simply as motions of material points, according to Newton's law of motion. The most unsatisfactory side of this system, apart from the difficulties involved in the concept of absolute space, which have been raised once more quite recently, lay in its description of light, which Newton also conceived, in accordance with his system, as composed of material points. Even at that time, the question, what in that case becomes of the material points of which light is composed when the light is absorbed, was already a burning one. Moreover, it is unsatisfactory in any case to introduce into the discussion material points of quite a different sort, which had to be postulated for the purpose of representing ponderable matter and light respectively. Later on, electrical corpuscles were added to these, making a third kind, again with completely different characteristics. It was, further, a fundamental weakness that the forces of reciprocal action, by which events are determined, had to be assumed hypothetically in a perfectly arbitrary way. Yet this conception of the real accomplished much. How came it that people felt themselves impelled to forsake it? In order to put his system into mathematical form at all, Newton had to devise the concept of differential quotients and propound the laws of motion in the form of total differential equations, perhaps the greatest advance in thought that a single individual was ever privileged to make. Partial differential equations were not necessary for this purpose, nor did Newton make any systematic use of them, but they were necessary for the formulation of the mechanics of deformable bodies. This is connected with the fact that in these problems, the question of how bodies are supposed to be constructed out of material points was of no importance to begin with. Thus, the partial differential equation entered theoretical physics as a handmaid, but has gradually become mistress. This began in the 19th century, when the wave theory of light established itself under the pressure of observed fact. Light in empty space was explained as a matter of vibrations of the ether, and it seemed idle at that stage, of course, to look upon the latter as a conglomeration of material points. Here, for the first time, the partial differential equation appeared as the natural expression of the primary realities of physics. In a particular department of theoretical physics, the continuous field thus appeared side by side with the material point as the representative of physical reality. This dualism remains even today, disturbing as it must be to every orderly mind. If the idea of physical reality has ceased to be purely atomic, it still remained for the time being purely mechanistic. People still try to explain all events as the motion of inert masses. Indeed, no other way of looking at things seemed conceivable. Then came the Great Change, which will be associated for all time with the names of Faraday, Maxwell, and Hertz. The lion's share in this revolution fell to Maxwell. He showed that the whole of what was then known about light and electromagnetic phenomena was expressed in his well-known double system of differential equations, in which the electric and the magnetic fields appear as the dependent variables. Maxwell did, indeed, try to explain or justify these equations by the intellectual construction of a mechanical model. But he made use of several such constructions at the same time, and took none of them really seriously, so that the equations alone appeared as the essential thing, and the field strengths as the ultimate entities, not to be reduced to anything else. By the turn of the century, the conception of the electromagnetic field as an ultimate entity had been generally accepted, and serious thinkers had abandoned the belief in the justification, or the possibility, of a mechanical explanation of Maxwell's equations. Before long, they were, on the contrary, actually trying to explain material points and their inertia on field theory lines with the help of Maxwell's theory, an attempt which did not, however, meet with complete success. Neglecting the important individual results which Maxwell's life work produced in important departments of physics, and concentrating on the changes wrought by him in our conception of the nature of physical reality, we must say this. Before Maxwell, people conceived of physical reality, insofar as it is supposed to represent events in nature, as material points, whose changes consist exclusively of motions, which are subject to total differential equations. After Maxwell, they conceived physical reality as represented by continuous fields, not mechanically explicable, which are subject to partial differential equations. This change in the conception of reality is the most profound and fruitful one that has come to physics since Newton. But it has at the same time to be admitted that the program has by no means been completely carried out yet. The successful systems of physics which have been evolved since rather represent compromises between these two schemes, which for that very reason bear provisional, logically incomplete character, although they may have achieved great advances in certain particulars. The first of these that calls for mention is Lorentz's theory of electrons, in which the field and the electrical corpuscles appear side by side as elements of equal value for the comprehension of reality. Next come the special and general theories of relativity, which, though based entirely on ideas connected with the field theory, have so far been unable to avoid the independent introduction of material points and total differential equations. The last and most successful creation of theoretical physics, namely quantum mechanics, differs fundamentally from both the schemes, which we will for the sake of brevity call the Newtonian and the Maxwellian. For the quantities which figure in its laws make no claim to describe physical reality itself, but only the probabilities of the occurrence of a physical reality that we have in view. Dirac, to whom, in my opinion, we owe the most perfect exposition, logically, of this theory, rightly points out that it would probably be difficult, for example, to give a theoretical description of a photon, such as would give enough information to enable one to decide whether it will pass a polarizer placed obliquely in its way or not. I am still inclined to the view that physicists will not, in the long run, content themselves with that sort of indirect description of the real, even if the theory can eventually be adapted to the postulate of general relativity in a satisfactory manner. We shall then, I feel sure, have to return to the attempt to carry out the program which may be described properly as the Maxwellian, namely, the description of physical reality in terms of fields which satisfy partial differential equations without singularities.